So my name is Joaquin Lopez. I've prepared some material for us to have some fun while learning a bit about reactive programming in C++17. So bear with me. These are pictures of three different systems. The first one is a regular spreadsheet application. The second one is a Japanese vending machine. I don't know if you're familiar with these machines. They're a lot of fun because in Japan you can basically buy anything from a vending machine. And the third picture is a civil servant sitting behind her desk. And I have a question for you. What are these systems doing most of the time? What are these systems doing? Take a look at them. What do you see? They do nothing. Yeah, exactly. Especially the civil servant. They're doing nothing. Or more precisely, they are waiting for some external input that forces them to do something, okay? If I change a value in a cell, all the dependent cells will change accordingly. If I press a button on the machine, then some internal gears will start working in order to deliver the item I asked for. If I go to the civil servant with, say, a form, the civil servant will take it in, stamp it, register it, handle me a copy of it, and then rest and do nothing, okay? So from a high-level perspective, reactivity is about systems being prepared to handle incoming data or information and process it as fast as possible in order to return to the steady state, to the do-nothing state, okay? Many applications, many programs can be modeled or thought of as reactive systems. Spreadsheet applications is like the prototypical examples, but also most GUI and user applications are basically doing nothing. They're just waiting for the user to click on a button or enter some text on a net box or something like that. So they can be modeled as reactive systems. I wrote, in order to learn a little bit about reactive programming, because I didn't know much about it, I wrote a small prototype library called Micro Reactive Programming, or MURP, or MERP for short. And this is like our Hello World example, our first example of using MERP to do some reactive stuff, okay? So I think the code is pretty clear. I'm declaring or creating two objects, x and y, of some undisclosed type value, initialized to 0. And then I define z as x times x plus 1 plus y plus 1. And then I set x to 6 and y to 5. Well, the obvious question is, what does this program output? What is the output? What is the answer? So, anybody guess? Well, you might say it's 1 because 0 times 0 plus 1 is 1, but in fact the answer is 42 because z is a reactive value. Z is prepared to change when x or y change. So what I'm defining is some sort of dependency between z and the source values x and y. This works for real. I mean, all the code you can download and you can play with it, etc. So, well, this is cool, right? Second example, it looks a little bit more like the typical reactive application. I'm not going to go into details, but let me just briefly describe how the thing works, okay? So I'm creating this trigger string s. This is basically an entity that whenever I assign it a new string value, it emits an event with this value, okay? And then I'm creating n that is connected somehow to s and transformed incoming strings into their sizes. Then e combines both s and n, both the strings and the sizes, filters out those elements where the size is less than 4, then via this map thing drops the size part and keeps only the string part and concatenates the resulting strings into a bigger string, okay? Then I connect a callback or slot, or in this case it is a function, a lambda function, that whenever some new string is emitted, it prints it into the console. And then I just fed some values to s. The result is this. Basically, I'm concatenating all the words whose size is greater than or equal to 4 to a bigger string, and each time the string changes, a new value is emitted to the console, okay? This pretty much look like a regular reactive application, if you're more or less familiar with RX, CPP, etc., then usually the stuff is created by combining chains of operations on event sources. Okay, we will learn how to implement this, and we will have some more examples about it. Okay. If you allow me a digression here, because I always like to talk about philosophical things, etc., I think the way I see it, innovation, much of innovation in programming languages depends on a very powerful mechanism called reification. Reification in general means turning abstract things into real things, or dealing with them as if it were real. In the context of programming languages, it means having concepts that you use when designing your programs turned into first-class citizens of a program, into entities that you can manipulate within the program, okay? Reification, as it happens, does not belong exclusively to programming languages, but it has a long tradition in the history of Western thought, in philosophy, mathematics, and I like to think that you can divide thinkers into two types, depending on how they see reification, or talking about abstract things as if they were real. There's the pragmatic guys who are like a little wary of talking about abstract things like they are stones or people, etc. And they're the idealistic fellows who basically are happy talking about universal things in any way they please, okay? So on the pragmatic front, we have Aristotle, or we have William of Ockham, who famously said, "Entia non sunt multiplicanda," which roughly translates to, "Don't make things up when talking about universal concepts." Or Grace Hopper, who is a co-inventor of COBOL and was a very pragmatic woman, I would say, when it came to designing programming languages. On the idealistic front, you have, of course, Plato, always Plato, or Cantor, who invented set theory. He talked about sets, or infinite sets, or transfinite sets. It was like crazy. He thought that set theory was revealed to him by God himself. So you see what kind of guys we're talking about. Or John McCarthy, who invented Lisp, and Lisp takes reification to its very extreme. Everything is a first-class citizen in Lisp. Data is lists, code is lists, you can manipulate code within the code, etc. So reification is a very powerful mechanism. And going back to a central topic, reactive programming is concerned about reification of two concepts. Again, the way I see it, incoming data and data processing. There's these two guys, Elliott and Hudek, who wrote a seminal paper on reactive programming some, 15 years ago or so. For incoming data, they proposed two models, two reification models, called, or I will call them, functions and events. So incoming data can be modeled as just a function of time, or in a discretized way as a stable value that changes from time to time, whereas events are modeled as values emitted at particular points in time. These two models are not competing with each other. They can be used in one particular scenario or the other, depending on your needs. And in fact, they can be used collaboratively also. If you review the literature on reactive programming, naming is rather vague. So functions can be referred to as behaviors or signals. And as for events, I have seen them named streams, observables. Here for the presentation, we will stick to functions and events. So this is a first concept that is reified, that is converted into some tangible entity by reactive programming. The second thing is data processing or control flow, or to put it in the same terms as Elliott and Hudek, declarative reactivity. When I say Z equals X times X, etc., what I'm implicitly creating is a dependency graph. There are some nodes that are connected to each other so that information flows from right to left. The dependency graph of the second example is basically like this. This graph is directed because information goes from the source to the sink, and it should be acyclic, because if I have a cycle on the graph, then bad things are going to happen. The information will keep looping forever, okay? So the cool thing about reactive programming is that control flow, which used to be something static, like you hard-coded the thing into the program, can be declared implicitly and at runtime. So these are the two main concepts of reactive programming. So far, so good? So as I said before, I wrote a tiny library in order to experiment with the main concepts of reactive programming and also to play a bit with exotic features of C++, 11, 14, and 17. My idea here is to spend like 15 minutes max in order to review a bit of the code. I won't go into much detail because I know you're tired, but I would like to point out some exotic or interesting C++ features and design insights that I would like to share with you. This is a Spanish bingo card. Take a look at it. Does anyone have it all? Like, does anyone here have the whole bingo? Have you used or are you familiar with each and every feature listed here? Please raise your hand. I'm sure. Even the people from the committee? A line? Does anyone have a line? Raise your hand. I have a line. Okay. Well, the library uses all of those. I will just explain or refer to the most interesting ones, okay? And of course, we won't be covering 100% of more. We are just going to review roughly 1/2 of the library so as to get the gist, okay? I'm providing visual clues. When you see this Caravaggio's painting on the slide, it means I'm talking about a C++ feature. The painting of Saint Teresa of Jesus is used to indicate design insights of the library. And I'm referring to code that is accessible in this GitHub repo. The name of the code can be found on the upper right corner. Okay? Good. As we are managing a dependency graph and there's information going from some nodes to some other nodes, I need to use some kind of library to implement this stuff, which is basically a signal slot library or callback library. There's a number of libraries like Qt, for instance. I decided to use Boost Signals 2 because it is convenient, because I am a Boost author, and because, well, I liked it, okay? Everything you need to know about Boost Signals 2 can be fit in just one slide. A signal is an object to which slots, which are functors or generalized objects with call operator, can be connected to, okay? So when I connect slot 1 and slot 2 to the signal, I'm returned to connection tokens so that I can manage the connection later on. And when I instruct the signal to emit a value, in this case I'm emitting X, then the different slots are called with that value, okay? If I disconnect one of the slots, subsequent emissions of a signal will only reach the slot 1. And if I disconnect slot 1, then I can continue using the signal, but no slot is going to be reached, okay? Simple enough. You understand it? Okay, good. So let's go back to a first example. I'm like removing all the syntax sugar having to do with declaring Z as a nifty formula of X and Y. Behind the scenes, what I'm doing really is this. I'm constructing a number of nodes, starting from the initial nodes, and then applying functions to other nodes, like multiplying the X by X, or summing W and Y, etc. So this is the same dependency graph as was generated on the first example, okay? And there's a couple of things here that might seem a little odd to you. The first one is value and function. These are not types. These are class templates. This seems like a bit shocking because this doesn't look like I'm using a template, okay? And this allows me to introduce one nifty C++ 17 feature called class template argument deduction, or CTAD for short. So the code I wrote before is as if I had written this, if I had provided all the necessary arguments, but the compiler is smart enough to deduce them, so I don't need to write them. Okay, in some particular cases, I won't go into details, in some particular cases, the compiler is not smart enough because it is not obvious what those types are based on the types of the construction arguments. For those cases, there's a thing called deduction guides that the programmer can use in order to make the compiler smarter, okay? The other thing that some of you might find a little odd is this multiplies bracket, okay? Usually it is multiplies int or multiplies double, etc. This is something that came in C++ 14 or something like that. It basically means when I'm not providing any argument, these function objects behave as generic objects accepting any type of argument. So it allows for a little tensor syntax here, okay? So you understand the snippet? So now we are prepared to basically know what the general layout of value and function class templates are, okay? So value is basically templatized with the type of the value that it holds, okay? Whereas in the case of function, I'm providing a modifying function of the dependent values and a list of nodes this particular node is dependent from, okay? And the rest of the interface is basically boilerplate, assignments for the case of values, the getters, connect for connecting external slots to these nodes, okay? And the operator pipe, which I'm going to talk about later on, okay? I had this design epiphany, like connectivity should be handled not by value or function itself, but can be factored out into a general base class that I named, that I called nodes, okay? So that the same thing can be reused by value, by function, and by the second half of MERP, which is the event part, okay? So this is using CRTP, and this allows me to define value as basically nodes of this and this, okay? Again, I won't go into details. As for node, this is the non-dependent version of node, that is node when no arguments are provided, a source node, okay? And the only interesting thing here is that I have a signal here. You see that the signature of the signal, the arguments that I pass to the signal, is a variant of things. I will talk about that. And when I connect the external slot, I'm not connecting the slot directly, but through an adapter that is using this visit overloaded stuff, okay? What am I doing here? What I'm doing here is basically I'm using the signal, I'm overloading the signal or using the signal as a kind of multi-lane highway so that I can use information, so that I can use it to convey information from node to node and also from value to function, okay? And the appropriate routing is done inside node. Again, I don't want you to understand all the details, but to understand now what I'm doing here. When I'm connecting external slots, I'm providing an adapter that basically filters out information that does not belong to this level. This first lambda over there means is meant for nodes and not for external users, okay? Another thing that I would like to point out is this nifty feature called variadic template multiple inheritance. It is very, very simple to inherit from a list of types. This was introduced in C++ 17, I think, okay? And this overloaded thing, which is using a deduction guide, allows me to very easily provide a function object that has different call operators, which is extremely useful for visitation, for use with tooth variants, okay, which is what I'm doing here, okay? And the other thing that I would like to focus on is to-deploy. To-deploy is the standard mechanism that the standard provides us with to unpack a tuple or a tuple of arguments and pass it to a function. When you're passed a number of a variadic argument pack, you can do two things: consume it immediately, or store it for later use. If you store it, you are basically, or most likely, you are storing the thing into tuple. And when you want to unpack the tuple and pass it to a function, you use to-deploy. Implementing to-deploy on your own is very tricky. So to-deploy is a very, very useful thing from the library, from the standard library, okay? A dependent node is basically the same as a non-dependent node with the addition of the dependencies, which is, again, a tuple of pointers to sources and some functions for connecting to the sources and disconnecting from the sources. Connecting to the sources is this like monstrous thing, okay, which is doing, again, connecting some slots that do the appropriate thing depending on whether the message is intended for node bookkeeping or for the derived classes, okay? And that's just one thing that I would like to focus on is what I call compile time iteration, okay? You see here that I'm doing this tooth making index sequence. What am I doing this for? Let me use this compile time iteration for a simpler example. This is the inner product. You already know what the inner product is, thanks to Guy Davidson. And I'm doing the inner product of two arrays, okay? In order to do this, in order to have this expression over there, A1 0 times A1 A2 0 plus A1 1 times A2 1 plus etc. I need to have the indices 0, 1, 2, 3 up to the length of the array. How do I do that? Okay, the standard way of doing this, and it's a bit tricky, but once you get used to it, it's basically the standard way of doing the thing is use this stud-make index sequence of n. This produces an object, an instantiation of a class template with indices 0, 1, 2, etc. up to n, and then I pass this to an overload or to another function that can use argument deduction in order to have this variadic pack of sizes. And this is what I can do to implement compile time iteration of the array. And this is what we have to do if we want to process sequentially a tuple or an array or something like that until the time that for ... comes, okay? That Axel was talking about, okay? So this is about nodes. Once we get nodes done, well, there's another thing I wanted to talk about, which is variadic fold expressions. This is an nifty thing coming in C++ 17. I have already used it for this. You see this plus times ... This is variadic dot expression. I have already used that before, but you haven't noticed. In this disconnect sources function here, I'm also using a variadic fold expression. It is a comma expression. You see it? This doing something with each of the elements of an array used to be very difficult to implement before C++ 17, like metaprogramming, crazy stuff, etc. Now it's reasonably easy, okay? And these enclosing parentheses are not optional. You need to have it, because otherwise the compiler does not know what you mean, okay? Once we have nodes done, implementing value and function is relatively easy, okay? For value, I'm just doing this assignment operator stuff. When I'm assigned a new value, I compare with what I have already stored, and if the value is different, then I ask my base class node to emit a signal. Simple, right? Operator pipe, we'll talk about that later. And function is not much harder. Basically, what I'm doing is whenever I receive a new value from a source, the node framework will call callback, and what I'm doing is updating the value that I'm calculating as a function of the values of my sources, and if the value has changed, I instruct the node class to emit a signal so that the information is propagated. Okay? Now the final part of value and function is this operator pipe thing. Operator pipe used to be something that nobody thought about, and now is much in vogue. Everyone's using like operator pipe for ranges or for everything. Operator pipe is in principle just syntax sugar. Okay, when I'm doing this auto y equals x pipe f, w y pipe g, etc., what I'm just doing is like in the 3 lines below. Okay, so operator pipe is just syntactic sugar. If I'm piping a function to a node, it's just like creating a node with that function dependent on the node that I refer to. Okay, the tricky part is when I'm cascading the operator pipe, and this is interesting. If I'm doing X pipe, F pipe, G pipe, H, in principle, what I'm doing is this, okay? But what's happening here is that the node that I'm creating with X pipe F is a temporary node. It doesn't have a name. So as soon as Z2 is created, these temporaries no longer exist. I have a dangling reference here. You see the thing? So what should I do there? In fact, what I want the framework to do for me is to create just one final node where the function is the composition of the functions in the chain. See that? In order to do that, I can resort to a feature of C++ 11, I think, that Juanpe already talked about, which is the ability to overload a function based on whether this is a temporary or not. So when this is a temporary, when the object is a temporary, the operator pipe should be implemented differently. So here you see the regular operator pipe. I'm passed a new function, and I'm returning a new node, new function object, okay? When I'm passed a new function, but I am a temporary, what I'm using is, I'm creating a new function, but I'm moving myself into that new function, okay? Got it? So this is basically it. With this, I can implement value and function. I think enough is enough. We have already seen some nifty, let's say, C++ features. What we haven't seen is how we handle the node copying and movements, and the second part of Merck, which has to do with events. But the thing is basically similar, okay? The library is really tiny. It has like 900 lines of code or something like that. Implementing something like that, even in C++ 11, probably would have taken like 3 times longer than this. So C++ 17, as I saw it, is very, very expressive. Let's play a little more with our new build toy. Before I was talking about the acyclicity of the directed graph. In principle, the graph is guaranteed to be acyclic because you are declaring nodes based on previously existing nodes. So there's an ordering between the nodes. But I can force cycles. Here, I'm basically forcing a cycle manually because x is whatever, y is a function of x, and then I'm connecting an external function that whenever y changes, plugs this value back into x. This is the graph. If I run this, what's going to happen? It should like crash or segfault or something. It collapses to a value. Very good.
I just saw the
Newton-Raphson. Okay, you're a very observant guy. Okay, well, this is a trick. Okay, I don't recommend implementing Newton-Raphson like this, but this is not segfaulting because it converges via Newton-Raphson to the root of this particular function, which is again 42. Okay, in general, you shouldn't be doing that. Okay, this is a bug in your program. Okay, another example has to do with how easy it is to create complex dependency graphs. Okay, again, it seems like everyone's talking about matrices, etc. So you already know how to multiply two matrices, and implementing this in a reactive manner is extremely easy. You have it here, okay? This allows me to talk about structure bindings. Are you familiar with the declaration of M00, M01 there? You know what I'm talking about? Well, for those of you who don't know what this is about, this, when S2 get 0, then is a tuple, okay? And when declaring this with the bracket thing, etc., what I'm asking the compiler is to extract the elements of a tuple and initialize the variables directly for me, okay? So it allows for a very concise syntax. I would like to have nested structured bindings, but the standard doesn't have it, and C++ 20, as far as I know, doesn't have it either, okay? And once I have this relatively complex dependency graph declared, when I change some value, like here, I'm multiplying two matrices with arbitrary values, I print it, then I change some of the source values, and I expect the affected values and only those to change accordingly, okay? And this is effectively what happens. I change M00, and only the first row of the result matrix changes, okay? Piece of cake. If we deal with the event flavor of MERP, this is a slightly more complex example of the kind of things we can do with reactive programming. Here we are using higher order events. What I'm doing here, I'm using a source of strings as before, okay? And I'm using group by. Group by is basically taking the input values and classifying them according to some user-provided function. And for each group, the group by emits a new event. So that when new values come here, these values are routed to the appropriate event. So I'm taking values, I'm outputting events. So what I'm doing in map, I'm transforming events, not values, okay? So this is like functional in nature, if you wish. What I'm doing is collecting the values coming from those events and using this hold convenience thing that basically behaves like a value. It allows me to retain the latest value emitted, okay? So I'm collecting the values inside each event, and then I am collecting also the events. So what I'm getting at the end of the day is a sort of container of values, okay? And with this double loop, I'm just querying for those values. What this thing effectively does is order or group the different names by its initial letter and then appending those to each, let's say, container, a vector or whatever, okay? And this is like, sounds so like, looks like a little odd in principle, but I mean, it is pretty standard stuff in reactive programming, okay? My last example is just for a bit of fun. Do you use Telegram? Yeah. Could you please search for this bot and send something, okay? So Manu, where's Manu? Well, thank you, Manu. He used the library in order to implement a Telegram bot, okay? The Telegram bot uses a Telegram library that basically feeds incoming data associated to a particular Telegram user or a Telegram bot, okay? By using this reactive programming library, he created this two-sided thing called bot that in one hand receives messages from Telegram and on the other hand routes or outputs those messages as if it were a MERP source so that we can use MERP to process the data. And what Manu has done is to create some processing on the data coming from bots in order to register new users or do something with some particular commands, etc. The good thing or the practical thing about reactive programming here is that it is extremely easy to add more behavior to the program by simply adding more and more sources, more and more, let's say, events connected to the source. So you don't have to change anything. I mean, it is completely decoupled. The information is completely decoupled from the way we process that information. This is what reactive programming is ultimately about, okay? Let's see whether you have reached the bot. Okay, so you are basically sending, and I hope that the bot is responding with some nonsense to you, okay? All the code is available to you if you want to have a deeper look or play a bit with it, etc. Okay. Well, thank you again, Manu, for the example because I couldn't have done that. Okay. I don't know how to program with Telegram or anything like that. I'm not a programmer really. And well, toys are just for fun. I wouldn't recommend using this tiny library for anything serious. This is just for learning about reactive programming and learning about C++17. If you want to use it, do it, but don't say me anything about it. In particular, what we haven't done in MERP, important things missing, is asynchronous or multi-threaded scheduling of data propagation. Everything is synchronous in MERP. Once I set the value at the source, all the data is processed in one fell swoop. Okay, serious reactive programming libraries have so-called schedulers that allow the programmer to specify whether this is done in a multi-threaded way, in the background, etc. Okay, another thing that MERP is not implementing, and this is important also, is event completion or error. Currently, MERP basically assumes an event is an infinite thing. It's going to keep on emitting values forever. It is more useful to have the notion of events terminating, because, for instance, you can concatenate events or stuff like that, okay? And MERP is not doing this. It could be evolved in order to support it, okay? If you want to do a fork and play yourself, let's do it. Let's see what the grown-ups have done. I basically typed reactive programming C++ in Google, and this is what I found. I found only two serious libraries, okay? The first one is React, C++ React. It is modeled about some concepts from Scala, okay? I would say it is a very reasonably written and sound library. It supports both functions and values. It doesn't support event termination or error. It is highly customizable when it comes to scheduling, etc. It uses Intel TBB. Sad thing about it, it seems to be abandoned from like November 2017, which is a pity because the library looks really good. So this leaves us with the only sensible choice, which is RxCPP. This is particularly appealing to those of you who are familiar with Reactive-X, which is a kind of multi-language interface for reactive programming that is then implemented in .NET languages, C++, etc. This is the brainchild of a guy called Eric Major, who famously invented LINQ, okay? So this is a very powerful library. Juanpe talked about the guy who implemented the thing, and a talk that I also recommend you see. The library is massively supported from a point of view of design. There's two things I don't like about this library. One of them is functions, values are not supported. It is all based on events. And function values are sometimes useful. The other thing is that the design is somehow clunky because it tries to conflate push and pull paradigms by using something called hot versus cold observables. Okay, so it is like a mix of reactive programming plus ranges, if I understood the thing right. And it goes through a number of contortions in order to do this reasonably looking. Okay, so once you get used to that, it is extremely powerful. And again, it is about the only thing you can use in order to do serious reactive programming unless you roll on your own library. So I recommend you basically study it and play with it, okay? And I'm finishing. I'm doing it in time. No, wait. Conclusions. The guy who started uploading doesn't know me because I always have a conclusion slide. So RP is about incoming data propagating through a dependency graph. From my point of view, reification is the real power behind reactive programming, the ability to use or talk about incoming data and data dependencies with first-class citizens within your program. This MERP library, of course, was just an experiment, but it's served us well, I think, in order to learn about reactive programming and learning about some nifty C++ 11, 14, and 17 features. I have to say that C++ 17 is tremendously expressive. Writing this library has been sheer joy to me. I had a lot of fun, and I know because I've been programming in C++ for, I don't know, 20 years, that doing the same thing with C++11 would have been much harder and would have resulted in less readable code. So C++17 really rocks. And that's basically it. Those are your options for reactive programming. My recommendation, if you're interested in it, is that you play with reactive programming, download RxCPP, learn, and don't be afraid to break things in the process. And that's basically it from my side. Thank you.
So thank you very much. Questions?
Yes. A little question. Qt has another signal-out functionality. It is the same that Boost is useful for?
Yeah. Basically, all signal slot libraries are functionally equivalent. Okay, I decided to use Boost signals too because I'm more familiar with Boost. But it would be extremely easy to port this morph thing so as to use Qt or Leipzig CPP. There's some other library for signals, etc. So yeah, the functionality required is like the very basic stuff.
Okay. Thank you.
No problem.
What an amazing, beautiful presentation. Congratulations. Really nice.
Okay, thank you.
One of the beauty of this is that future compilers that are really powerful can optimize much of this away. What do today's compilers do? Did you look at what comes out of this? How much of this gets actually inlined? How many of the call frames do you actually lose?
That's a very good question. Problem with this is, okay, there's a lot of things that can be optimized, but this is already done by the library itself. Like here. This is basically what gets optimized, okay? If you're declaring a long chain of operations, all of this is optimized into just one big function, and the compiler is free to basically enter there and optimize away everything, okay? This is the easy part. The hard part is the connection between nodes. This is runtime information. I don't see how the compiler can possibly optimize this away. So I think you have some like intrinsic overhead you cannot get rid of. That's my intuition, at least.
Thank you. More questions?
Okay.
Oh, sorry.
Pump it.
First, thank you very much. It was a great presentation and an excellent library, actually. I really enjoyed it and learned a lot from it.
Thank you.
Also, thank you, because I learned today that Joaquin is the author of the Boost Multi-Index Library, which I mentioned tangentially in my talk, so I wanted to give some props for that. And actually, more than a question, I wanted to maybe connect a little bit the two talks with a little reflection. Probably it was already evident, as you mentioned, RxCPP, which I mentioned at the last part of my talk, but I really see this as a great way to cover this notion of an existential value that represents a dynamic entity from the world that changes in time, even contains things from the future that we don't know about, and that is a dualistic aspect where I think part of the API is really value-oriented, right? So I think insofar we talk about the compositional operators like map, filter, and the piping, you're just declaring what the transformation is, and then at the very end, you bring it to a reference world when you do a connect, and then you're bringing a concrete observer, which is in memory somewhere, reading concrete values, right? So I think, just wanted to make this mention so people can think a little bit about, okay, how to represent values or complex dynamic systems in values. I think this talk showed a great way to do this. Yeah, thank you.
Yeah, well, I don't have much to add. I'm also a functional programming junkie. And I had the privilege of knowing what you were going to talk about, because I had your presentation already on YouTube, so I knew that some connections were going to be made. So yeah, functional programming, I think much inspiration can be drawn from functional programming in order to evolve C++. Just a couple hours ago, we also talked about something for you to think about. I don't have an answer for this. This is just like a kind of challenge. We are like using operator pipe everywhere, using chains of transformations, functional stuff, etc. And it seems to me that it's pretty obvious that there's a grand unifying theme around ranges and reactive programming and coroutines and monadic stuff, etc. And no one else figured out yet how to tie this into some coherent framework. If you take RxCPP, it's kind of trying to do both ranges and observables in a clunky manner, I would say. But I think the following years we will learn how to compose all of this together into something that is bigger than the sum of its parts. Let's see what the future looks like.
Thank you. Any other question? I think, oh!
Yeah, I have a question regarding the loop,
The what?
the Newton-Raphson method.
Oh, yeah.
If it didn't converge, would you be in an infinite loop? Just so I understood.
No, the stack will be
Oh, yeah.
running up.
Yeah, of course.
Stack overflow.
Okay.
Yeah.
Okay.
This is what
Thank
would
you.
happen. No problem.
Thank you.
Well, this is, just to give a little more information, this is because this is synchronous. If you're using a multi-threader or scheduler, it would keep looping forever. This is what would happen.
Okay, Joaquin, thank you very much.
Thank you.